Okay. So, in the last class we have discussed about the characteristics of a PLL and how it can track phase and frequency error. So, we have seen that just by giving a first order filter which is Hs equal to 1 within the band of interest, it is a low pass filter of course, because it has to reject that higher frequency term. So, if that we give, we could see that it tracks frequency very nicely. So, basically it exactly tracks the frequency. In phase it gives a constant phase error. Okay. So, this is what we have already observed, right. So, now what we wish to do is, can we better this? So, our next target should be, we will take a Hs which is of second order. So, let us say the transfer function is something like this, S plus A divided by S. So, this is just a realistic filter, we can design it with any RC circuitry. So, that is possible. So, let us say we will take this. So, immediately what will happen, by theta Es, which is nothing but this S divided by S plus A k Hs. So, in place of Hs we can write S plus A divided by S, that is my Hs, into theta Is, which is omega 0 minus omega c divided by S square plus phi 0 divided by S. This is something we have already proven. So, we have said that it is the similar kind of input which is coming at a different frequency of omega 0, not exactly matching with the free running frequency, and it has a constant phase. If that is the type of input, of course, if it has something other than this characteristics, we will have to do something else. Okay. As long as this is something which is happening, that the exact frequency I do not know, there is a deviation and there is a phase, that phase is whatever that phase is, that remains same, that is not a random phase. Okay. So, as long as this is happening, we have the error signal as this. Okay. So, let us simplify this little bit. So, we get this should be S square and then S square A plus A k S plus A, and we have omega 0 minus omega c S square plus phi 0 by S. Okay. And most of you have learned Laplace transform in network theory, you might have learned the final value theorem. So, instead of doing this, suppose I want to evaluate that theta E at plus infinity, right. So, that I can do by evaluating theta E t and putting limit t tends to infinity. Same thing is equivalent to, if I just have S domain representation, theta S multiplied by S limit S tends to 0. So, that is the result of final value theorem. So, we will be utilizing this. Our target is to evaluate at time tends to infinity what remains, what is the phase error that remains, that should be my final phase error. So, let us try to evaluate this part. So, if I just do that, you can see that if S tends to 0, I am multiplying by S. So, for this term S square gets cancelled, S tends to 0, this will have some value, but I will still have a S. If I just put that S tends to 0, this particular part will go towards 0. Same thing will be happening over here, because here only one S will be cancelled. So, there is already one S, another S will be coming from here. If I put S tends to 0, that part also will go to 0. So, this must be equal to 0 if I put S tends to 0. Okay. So, my final value is 0. So, now you can see very nicely, if I put a second order loop filter, okay, immediately frequency has been tracked. I know that because the way I have represented already, it is in the input this one, the means or the VCO generated one will be exactly tracking that omega 0. Okay. No problem in that. Even in phase also there is no error. So, it tracks the phase exactly accurately. You might be arguing there is a sudden difference. The way we have, if I just give you that one of the earlier example where we were putting the VCO circuit. So, if you see, whenever my phase error is 0, that means this is exactly tracked, okay, no problem in that. But the problem that will be occurring is this is sine and this is cos. So, there will be, no matter how well you track the phase and frequency. So, if you exactly track the phase and frequency, there will be a pi by 2 phase shift. So, if you wish to use that VCO output as a demodulator, you have to give another pi by 2 phase shift to that particular thing. So, this is absolutely mandatory, that you will have to again from cosinusoidal you have to translate it to sinusoidal or sinusoidal to cosinusoidal. You will have to do that, because their input whatever phase it has, there will be, after complete tracking of the loop, there will be a pi by 2 phase shift. That is something we can see. If this is sine, this is cos. Okay. So, that pi by 2 phase shift has to be somehow eradicated, and that can only be done by employing a pi by 2 phase shifter again after the VCO. Okay. So, whatever VCO output we get, that is completely asynchronous with the incoming this one, barring a pi by 2 phase shift. So, now I can employ that pi by 2. So, earlier whenever we said there was a phase difference of that omega 0 minus omega c by a k when we were putting a first order loop filter, that means that was already there, plus there will be another pi by 2. Okay. So, that was the overall phase shift, whereas here the phase difference has been tracked completely. So, you have exactly pi by 2 phase shift that has to be somehow taken out from the circuitry whenever you design your VCO, right. So, this is what we have now designed. Now, you can just play around with it. You can actually show that if suppose whatever that we have written, it is this a sine omega 0 t plus phi 0, we have written this, right. Now, if your this omega 0 also varies with time, let us say it linearly varies with time. So, of course, in modulation that will not be happening, but for some reason for a particular amount of time, if that is the case, your first order will not be able to even track it. So, even frequency tracking will not be happening, that will fail. You can immediately prove that you will not get to a final value, that will still oscillate. So, you will not be able to track that, whereas your second order will track that, but there will be a constant phase shift, you will be able to prove that. Similar method you just employ, just put omega 0 as a linear function of time. Okay. So, if you just do that, you will be able to show that. Second order will actually give you a constant phase shift, whereas if you now go to third order filter, so higher the order, probably the tracking becomes better and better. So, if you put a third order filter, you can prove that it will track the phase and frequency completely. So, that is something which will be happening, but remember this entire analysis has been done for a small error signal or small phase error signal. So, if that is not happening, you probably cannot argue about these outcomes. Okay. So, this will be always happening as long as the phase and frequency are almost synchronous, that means they are very close to each other, just there is little bit of deviation, and we know that even a little bit of deviation can be detrimental for our demodulation. So, we wish to make it completely synchronous, that is why this PLL is being employed. Okay. So, now we will try to see that part if there is a deviation. Okay. So, let us say I have a loop filter, okay, which is equals to 1. Okay. So, the loop filter is just that first order filter we were trying to employ. Okay. So, this is something we are assuming. Of course, it will have a low pass characteristics, but what we can also assume that that 2 omega c is very high. So, I can almost assume it to be a band pass within the band of my interest, and then accordingly I can write this h t to be a delta function, right, because that is just the inverse Fourier transform. Okay. So, h s is 1. So, therefore, h t will be just the inverse Laplace transform of this one. So, that should be delta t. Okay. So, this is what we get. Now, we do not actually put that sin theta equals to theta, because right now whatever analysis we will be doing, that is not good for, means hold good for the small signal analysis. Let us assume this part. Okay. So, if this is the case, what we can write is, we can write that our equation. Okay. So, the equation is, if we just go back to our filter, or even the previous one. Okay. So, if you just go back to this, so there is a sinusoidal, after that I am just putting AK, Hs is becoming 1, right, because that is what I have employed. Okay. So, if there is a sinusoidal, then I cannot really call that as theta e, I can just write that as if that is a sinusoidal of theta e multiplied by AK. So, that should be faded over here. So, my theta output derivative should be that one. Okay. So, I can write immediately that theta output t, the derivative of that must be AK sine of theta e t. Can I write this? Okay. So, that directly comes from that phase model where no approximation is being taken now. Earlier we were taking an approximation, we were saying sin theta e t is equivalent to theta e t, that was the approximation we were taking. Now we are not taking any approximation. Okay. So, we are just saying according to this particular phase lock loop, whatever means from the phase perspective, whatever linear circuitry we have or nonlinear circuitry we have put, this should be the case. Okay. So, that is fine. If this is the case, now I can also write my, let us say, incoming phase like I was writing previously. So, that should be omega 0 minus omega c into t plus phi 0. So, this is equivalent. Earlier whatever I was writing, that it is coming at omega 0 t plus phi 0. So, if I just compare it with the VCO free running, then the phase input phase, which is actually theta I t, that must be equal to this, we have already done that. Okay. So, this is that phase. Now, let us try to write what is the theta e. So, theta e is basically theta I t minus theta O t, right. Now, I can derive, means take a derivative over here. So, immediately theta e t derivative, that becomes theta I t derivative minus theta O t derivative. Theta I t I already know, the derivative of that should be omega 0 minus omega c, because it is just linear of time, and theta O t derivative I already know this. So, that must be A k sine theta e t, fine. So, up to this there is no problem, I can write that, write this one in this fashion. Okay. So, once I have got this, now what I can do, because we do not want to, now the solving part will be difficult, because there is sinusoidal and then a derivative of that, solving will be a little bit difficult, but we do not need to solve it, we can actually say something about it. So, let us try to actually plot theta e t and means theta e derivative with respect to theta e t, let us plot that. Okay. So, if I just plot that, it is just a shifted sinusoidal. Okay. So, it will look like this. Whereas, it will be touching at 0 at omega 0 minus omega c, because see this is where theta e t derivative I am plotting, and this is where I am plotting theta e t. Whenever you put theta e t equals to 0, you get theta e derivative t as omega 0 minus omega c. So, this must be cutting, because at that point theta e t is 0. So, this must be cutting at this point. Okay. And this particular value, how much is this? That should be omega 0 minus omega c minus A k, the maximum of the amplitude, right. Okay. Now, let us try to see where exactly I will get that phase lock, okay, or equilibria. So, equilibria means at the input to the VCO, I have a constant thing, it is not changing. Okay. So, that means this theta e t derivative, that is equal to 0, because that was the input to the, if you see that is the input to the VCO, right. This was the input to the VCO. If that is the input to the VCO, if that input is 0, that means there is no point in changing the VCO. Now VCO is locked. So whenever that input becomes 0, that is where it will be in equilibrium. Okay. So whatever that is. So whenever theta e derivative is 0, I know that those are the equilibria point. Now let us try to analyze where those equilibria points are. Theta e derivative is on the y axis. So wherever it crosses this 0 in y, those are the equilibrium point, right. So this must be, let us mark them. Let us say this is actually theta 1, this is theta 2, this is theta 3, this is theta 4, right. Like this there will be, if I just keep on going, there should be a theta 5 and so on, and theta minus 1, minus 2, like that, there will be many. Okay. So there are infinite equilibrium point in this case, that is something we can see already. Now we have to see whether these equilibriums are stable or unstable. Okay. Stable means, what is stable equilibria? That means you give a perturbation, that means you deviate it little bit, it will try to come back to that same equilibria. Okay. So that is a equilibria, and even if you perturb it, you just deviate it, it will again try to track it back. And unstable is, it is in a equilibria, you perturb it, it will go away from that. Okay. So it will go further away again, it will again keep tracking and go away from this. So those are the stable and unstable equilibria. So let us try to see that. Okay. So let us say around this there was a initial phase error. Okay. So see, whatever happens, because I could see that the overall phase trajectory should be on this. So it should be moving on along this. Whatever happens, the loop equation actually gets bounded over there. So it must be actually moving around that sinusoidal. This is what should be happening. So let us say initially I have a phase error, right. So that phase error, let us call that as theta 0. Okay. So this was theta 0. At that point, what is the derivative? That is negative, right. So the derivative of that is negative. So immediately what it will try to do, because the derivative is negative, it must be trying to lift that phase up. Okay. So that particular part. Okay. So because the derivative is negative, it will try to negate that, it will try to go towards that 0. Okay. So if that happens, then immediately what will happen to the phase? It can go up only in this direction. Okay. That derivative can go up only in this direction, it is going towards 0. Okay. So if that happens, the phase is actually getting reduced, and it is, whenever you put a phase over here, it will always try to go towards this. Same thing will be happening over here. If you just put a phase error over there, it will actually try to track it back to this equilibrium. So that is why I can see that even if I am at that equilibrium, I give a perturbation, it will always be coming back to that particular equilibrium. So I can immediately call that equilibrium to be a stable equilibrium. Okay. So this is happening to be a right. Whereas you can also test this or this equilibria, you will see that they just go away. Once you put over there, in those equilibria, if you put a perturbation, okay, immediately you will see it will just take it on the other side. Okay. So it will just take it away from the equilibria. So you can immediately say that probably in this particular equilibria it is locked. Okay. So that will be happening. So this is, for me, theta 3 is a stable equilibria. Okay. At theta 3, what will be happening? So I had a guiding equation, right. So the guiding equation was theta e dash is equals to omega 0 minus omega c minus a k sin theta e t. Right. at theta 3 this must be 0, that is what we are seeing, that at theta 3 it is a equilibria, that means the derivative must be 0. So, this I can put as 0. So, 0 is equal to omega 0 minus omega c minus a k sin theta 3, or I can write sin or theta 3 is equal to sin inverse omega 0 minus omega c divided by a k. A very nice thing has happened. If you now see what has happened, if this is pretty small, that means omega 0 minus omega c divided by a k is much smaller than pi by 2. I can write this theta 3 almost approximately equal to omega 0 minus omega c divided by a k. Remember what was the filter I have put? It was HS, first order filter. In first order filter, when we did for a small signal analysis, the final value means we put the final value theorem, or we put the at t tends to infinity what will be the phase error, that was this exactly. We are again, when we start putting this particular approximation again, that this is much lesser than, or the phase error is much lesser than pi by 2, we again see that we are getting back the same result. So, it is all consistent, but what we also see that here probably you can tell about more on equilibria. So, what kind of equilibria we can get? Earlier we were just solving for one equilibria, because we are already saying that it is very closer, okay. It is much lesser than pi by 2. So, we are already in this equilibria and we are trying to solve that, okay. Whereas, here if you see, we have multiple, almost infinite number of equilibria, and we can immediately see that half of them are stable equilibria and half of them are unstable equilibria or non-stable equilibria. So, this is something which is happening over here. So, this is the extra thing you can say, and there also, because for any this approximated analysis, if you do the general analysis from there, if you again put back the approximation, probably you should be getting back the same result. So, that is what we are getting, okay. So, this characterizes the PLL, means almost in little bit of greater details. Of course, there are other means nonlinear analysis of this one, but that probably will not be required for this course. But here at least we have understood what can happen to this particular PLL, when it can track the frequency or phase, what are the condition of doing that, all those things. Here also you can also see that, see when, if you just try to see this curve where it crosses means what is the minimum point, that is actually omega 0 minus omega c minus a k, okay. So, it is actually omega 0 minus omega c minus a k, right. So, this is what we are getting. So, for some reason, if this particular sinusoidal goes above the 0th axis, okay, or above the x axis, will you have any equilibria point? Will not have any equilibria point. So, that means there is a condition on this omega 0, omega c and a k, which are the parameter of incoming whatever phase you are getting or frequency you are getting, and the PLL free running frequency as well as some of the parameters of the PLL, okay, like k. So, as long as these things, this must be less than 0, okay. If this is happening, then only you will have a tracking of PLL, right, otherwise not, because otherwise whatever curve we have put, it will just go above x axis and there will be no actually cutting point where your PLL, that theta e dot becomes 0. If that is not 0, then the VCO input will not be 0. So, it will keep on changing the output, right. As long as there is something at the input of VCO, VCO will keep on changing the frequency. So, there will be no lock that will be achieved through the PLL. So, to achieve lock in PLL, I need to have this sinusoidal coming below 0, and for that I need this condition, or I should say omega 0 minus omega c must be less than equal to AK. Okay. Or we should actually write the modulus of that, because it might happen that omega c is greater than omega 0. So, that might also happen. Whatever happens, it should be this. Okay. So, that condition should be always satisfied. So, and that relationship must be there to get a lock in the PLL. So, which also says that your frequency should not be too much deviating from the targeted phase lock loop free running frequency. So, that should be the case. You cannot really hope to track back a particular input sinusoidal phase and frequency when your PLL is deviating, that PLL has a VCO and VCO free running frequency is deviating too much. So, that is a ill design, that you know your carrier is at 500 megahertz probably, and you come up with a PLL which has a free running frequency of 5 megahertz. It does not make sense. It must be around that 500 megahertz. You know that exactly I will not be able to track, but it must be around that. So, I say that I will be creating a 500 megahertz, but of course, there will be a deviation because of manufacturing and all those things. So, if this is 500.1, this might be 499.9, something like that, and then the rest of the things it can track, and that is very clear because we need this, otherwise we do not have a tracking. Okay. So, this probably ends our discussion on PLL. So, we have seen the effectiveness of PLL, we have seen what are the design criteria of a PLL, what are the things we need to do, and what are the consequences if we can't track it properly. That is also something we have already seen. It is a very important integrated circuit, so which should be studied in depth. Okay. So, what we will do in the next class is we will try to see in a DSB-SC demodulation how this PLL and the squaring of the signal, which is the overall thing for carrier recovery, can be a very nice way implemented. So, there is a famous circuit called Costas loop. We will try to exploit that part. That actually gives you a practical DSB-SC demodulator, not just a multiplier, because for multiplier we need to assume that there is a complete tracking of phase and frequency. So, what we will be giving is a realistic practical circuitry. So, we will try to see how the concept of PLL is almost being employed over there. Okay. Thank you.